Welcome to the Ultralight Airplane Workshop. I'm Leon. This video is the second part of a two-part or possibly a three-part, I'll talk about that a little more in a moment, video on selecting an airfoil for an ultralight airplane that we're designing. We're calling that airplane the UWS-4. This ultralight airplane falls under Part 103 regulations of the United States Federal Aviation Administration. In part 1 of this little series, we went over what we're going to look for in an airfoil to use on our ultralight so that the airfoil and the airplane itself will meet the requirements of the mission that we want for this ultralight. Now for this ultralight, it's more of a cruising ultralight. And what I mean by that is instead of just flying around low to the ground looking down, it's really more intended to fly to local airports so I can visit friends and then fly back home. So I need a little more range. And to get that more range, we need less drag. And so that's one of the important parts we're using in selecting this airfoil. If you haven't seen part 1, which is actually called Part5 A, now I'll put a link up here in the upper right hand corner you can go to and watch that video. That'll explain a little bit more about what we're going to look at here in this video. And speaking of that, in this video we're going to go through analysis that we talked about in Part5 A, and then actually select the airfoil we're going to use. If you've not seen any of the videos in this series yet on the design of the UWS-4, I'll put a link up here in the right hand corner to a playlist so you can see all the videos that we've had so far. Now let's get to it. Okay, so what we have here is coefficient of lift versus coefficient of drag. And by the way, if you're not familiar with the terms coefficient of lift and coefficient of drag, I'll put a link up here in the upper right hand corner for a playlist of aerodynamic terminology videos. And in that list you'll find a video for coefficient lift, another one for coefficient drag, and some other terms that you'll also find in this video. And if you decided to skip looking at Part 5A, you should know that the program that we're using here is XFLR5, and there's a link down in the description of this video that you can go to get to this free airfoil analysis program. So what we want to do is find out how much drag do we have at various lift coefficients. Now if you remember, we were looking at a lift coefficient at cruise of about 0.6 to 0.5, somewhere around in there. So let's zoom in on that, because I want to look at the drag at that lift coefficient. Now we have the same colors as before. This purple one is that NASA one, the laminar flow one we were looking at. And so you can see from about 0.75 down to about 0.25, we're in something called a drag bucket. You can see the drag suddenly gets much smaller down in here in this drag bucket area. And that's a characteristic of a laminar flow airfoil. Now which one has the worst one? That's this red one here, and that's the Wortman. So the Wortman has the worst drag. The next one is the Clark Y. This yellow one is a Clark Y, so it's the second worst one. This blue one is Harry Riblet's airfoil, so it's kind of in the middle of the pack. And then this green one is my airfoil that I designed. So out of the turbulent ones, at least at our cruising coefficient of lift, the airfoil I came up with has the best drag. Now another thing that's kind of cool, look at Harry Riblet's airfoil. This one's kind of odd. It seems to have a drag bucket right up in here, unless there's something funny going on with how XFLR5 is doing the calculation. See how right here at 0.75 it suddenly reduces its drag? Especially compared to the other turbulent airfoils. That's very interesting. It's almost like there's a drag bucket right in here at this higher coefficient of lift. So if you were going to have your airplane operating somewhere up in this coefficient of lift during cruise, Riblet might be a good one if you're concerned about drag. Now, one thing that Dan says is if your coefficient of lift at cruise is higher than 1, you've probably done something wrong. You really don't want to get too close to this coefficient lift of 1 during cruise. You may have to make your wing service area bigger in order to get down to a more reasonable coefficient lift. Now, this area up in here is also interesting when you're climbing, because you're going to usually be at a slightly higher coefficient lift as you're climbing. Your speed is going to be lower, which means you need to have a higher angle of attack, which means your coefficient of lift has to be a little higher. So you're probably going to be climbing at maybe 1, 1.1, 0.9, somewhere in this area. So if for some reason you're really concerned about your drag when you're climbing and you want to have low drag there, then you'll actually think about this coefficient of lift area somewhere up in here. So that's our coefficient of drag. Let's look at our coefficient of lift. So here's our coefficient of lift. Now I did the calculations from 8 degrees up to 25 degrees. Now you can see on the Workman, it actually had a little bit of a problem here at 20 degrees. It wasn't able to do any more convergence after that, but that's okay. We don't really care about that. Now here's something that surprised me about the Clark Y. Now remember, the Clark Y is the yellow one. You can see up here at stall, at the maximum coefficient of lift, after that stall, it actually starts dropping off fairly rapidly. It's not horrible, but I did not expect this for the Clark Y. I expected it to be a much broader curve. For example, on the Harry Riblet airfoil, look how broad this curve is. It actually comes down slowly out here, which means when it stalls very gently. As you keep increasing and increasing that angle of attack, it starts losing lift, but it's not abrupt. It's very gentle. And you can also see that here with the Airfoil I design. It's a very gentle fall off in coefficient lift as you're increasing your angle of attack. Now the Workman appears, at least up to 20 degrees, to be doing the same thing. Past 20, I don't know. I don't know if it's abrupt fall off, but I doubt that it is. Now look at the NASA Langley airfoil. It actually isn't horrid. It doesn't have as broad a stall, but it's much better than I thought it would be. But it really makes sense with that really rounded nose that it has on the leading edge. It's kind of unusual for a laminar flow airfoil. Now let's look at the maximum coefficient lift. Now remember, this is at cruise speed. So you would only encounter this stall, for example, if you were in a really steep bank and pulling back hard on the stick. That's when you might encounter this stall here. So we can start to get an idea down here what the angle of attack is going to be when we're cruising. So let's zoom in on that. So we're looking at a coefficient lift of roughly 0.6. So you can see that the angle of attack on the Clark Y is going to be the highest. It is at, you can see the coordinates up here. So let me put my cursor on that, and you can see that coordinate is a little over 2 degrees, 2.17 degrees. Now both my airfoil and Harry Riblet's airfoil are about the same location. That's about 1.5 degrees. The Langley airfoil is just almost at 0. And then the Workman is way over here. It's actually at a negative angle of attack of roughly 3 degrees. And that's just because of that huge cusp that's on the trailing edge. It's like having a built-in flap. And so it's actually going to have angled down because it's going to have so much lift there. So that's why you have to have such a nose-down attitude. Now, let's go look at coefficient of moment. So here is the coefficient of moment. Now you remember, the lower the coefficient of moment we have when we're cruising, the smaller that tail can be, and the lighter our airplane can be. And in addition, less drag. So you come down here and look at this Workman, that is huge. That's a huge amount of coefficient of moment. Even over here, what is it, -3, which is right there, so that's where we'd be cruising. That is a massive coefficient of moment. We've got to have a really big tail, almost 3 times what we need for these 3 airfoils down here. So in order to make a light ultralight, I would not use the Workman strictly because of this massive coefficient of moment. It's got a great maximum coefficient of lift, but it had pretty high drags. So it's really got 2 strikes against it. It has the worst drag and worst coefficient of moment. For my airplane, where I'm wanting to have a long, efficient cruise, I would not use the Workman. So I think we can ignore that one from now on. So what's the next worst one on coefficient of moment? Well, it's this Langley airfoil. It's got a fairly high coefficient of moment. Now it cruised at roughly 0 degrees, a little bit more than that, about half a degree. So at half a degree, we're down here at almost 0.13. So that's about, 50% higher than these, roughly. So that's not horrible. If you thought you really had put a high priority on this low drag here, and you thought you would be in the laminar area, and you like this high coefficient lift here, then the Langley may not be bad. If you can tolerate just a little bit larger tail to counter this coefficient of moment, and you really wanted low drag, then this might not be a bad solution. I would probably only use this for a composite airplane where I can have a nice, really smooth skin. I would not use this for like a fabric covered airplane. You're just not going to get the smoothness you need. Most laminar flow airplanes need a very smooth skin, and in particular, you have to have a really, really smooth nose. Now, if you fly when I do, which is frequently at sunset, you're going to get a lot of bug splatter on your leading edge when you're taking off and landing. And that bug splatter can frequently disrupt laminar flow. So you can actually lose your laminar flow within a couple hundred feet of leaving the runway. In that case, you're going to have large drag and you're not going to have that maximum coefficient of lift. You'll lose a lot of the advantages of this NASA Langley. If you're flying in the middle of the day, you got a composite wing, and you don't mind having a larger tail, the NASA Langley might not be bad. Now, my current plan is to use an aluminum wing. So I'm going to have a lot of rivets in there that can disrupt the boundary layer. And I'm going to be flying in the evenings where I can get bugs on the leading edge. So I'm not going to use Langley. So now I've gotten rid of this airfoil and this airfoil from consideration. So that leaves these three, the Clark Y, my airfoil, and Harry Riblet's airfoil. Now, as far as coefficient of moment goes, man, this Clark Y, it has a fantastic coefficient of moment. You can make a nice small tail. Let me review where that cruse angle of attack was again. So these are all fairly close together. 1.5 up to 2 degrees. Okay, let's go back. So there is 1.5 there, and 2 degrees is there. So the Clark is a little bit better. Let's go back and look at drag again. So it's got the second worst drag. And let's look at lift again. It has reasonably good lift. I'm not as fond of this stall out here, but it's not horrid. So it's not a bad airfoil to select. I think it's reasonable. So let's look at Harry Riblet's airfoil. So it looks like it's almost identical to my airfoil here on coefficient of moment. Yeah, it really is very close. 1.5 degrees right there. They're almost identical here at cruse. When you come out to the stall, Harry Riblet's is much less, but I'm not as concerned about that. So at cruse, should have the same tail drag from both Harry Riblet and my airfoil. Now let's go back and look at drag for the airfoil itself. So mine is slightly better than Harry's here at cruse. Let's go back and look at lift. So here's Harry's in blue, mine's in green. So mine has higher lift. The angle of attack of mine when it stalls is slightly less than Harry's. Harry's has a little bit higher angle of attack at the maximum. Mine has a little bit better of a fall off here in the stall area, post stall, than Harry's does, but not much to really make a difference. I don't think considering that's probably relevant. But this maximum coefficient lift here at cruse isn't quite as important as it is when we're landing at 24 knots. So let's go ahead and take a look at what happens with flaps deployed on our airfoils. Well, we'll start with all of them, but I think we can probably quickly eliminate the NASA airfoil and the Wortman. Let's take a look at those. So these are our airfoils that have 40 degrees flap. And again, we're looking at our coefficient lift versus coefficient of drag plot. Now, I don't think that looking at this particular plot makes a whole lot of sense. We're actually trying to come in and land here. So we actually want a whole lot of drag, typically, to help us slow down. And all of these have really high drag at their maximum coefficient lift. Now let's go look at the lift. So here's our coefficient lift with our flaps deployed to 40 degrees. So let's see who has the maximum. Well, the maximum is the NASA Langley. It's got fantastic lift. It's up at about 2.22 nearly. So that's actually a fantastic coefficient lift. If you thought you really wanted to have a high lift airfoil, but be laminar, this NASA Langley one would be pretty good. But again, remember, at cruse, you've got that massive coefficient of moment to deal with. So I don't want to deal with that, so that is still eliminated. And again, let's look at the Wortman. Now, this is very, very interesting. If you remember, back when we were looking at our cruse or unflapped condition, that Wortman has a pretty high coefficient lift. But once you stick in those flaps, it is almost identical to the Clark Y and my airfoil. Now that's very, very interesting. Now that really tells me that the Wortman is not intended to have flaps added to it. Flaps don't really gain you much at all on that one, at least over the others. That delta change in lift isn't as much for the Wortman as it is for the others, basically because it already has built-in flaps. Let's take a look at the Clark Y. Now that's kind of interesting. See how the Clark Y still has a bit of a fall off here after the stall, even when it's using flaps, which is, I find, very interesting. Now here's another thing that I'm not quite certain how to analyze. On my airfoil, it suddenly had a terrible, terrible time trying to converge. So I don't know if we can believe this out here or not. Now when I've decreased the flaps a little bit to like 35 and 30 degrees, this drop does not happen at all. So I'm not sure if this is believable or not. The rest of it I really, really like. It's got a fantastically smooth curve, very flat over a really wide angle of attack up here on top. And let's see, that maximum coefficient lift is basically 2.12, something like that. So that's not bad. Now it's above that 2.0 that we needed. But keep in mind, our flaps don't go full span, so our coefficient lift, our wing is going to be less than this. We lose some coefficient lift because it's a finite wing, so the flaps overall, even if it were full span, will probably be a little bit below 2.0 for a real wing. Remember, this is actually not for the wing. This coefficient lift is for the two-dimensional airfoil itself, not the wing. And then let's look at Harry Riblet's airfoil. Now Harry Riblet's, his maximum coefficient lift is quite a bit lower. It's not horrible. It's coming up to 2.0. So it's not too far from this. 2.12 down to 2.0. So it's still a fairly good performing airfoil. The fall off after the stall is still pretty good. So it's still not a bad airfoil. Let's go ahead and take a quick look at coefficient of moment. As you'd expect with the flaps deflected, you got a far higher coefficient of moment. Remember, we were up around 0.08 or something like that for the airfoils we were really interested in, and now we're way down here. Now Harry Riblet's still has the best coefficient of moment. And then the Clark. And then amazingly, the NASA Langley is actually doing pretty good out here at stall. And by the way, I'm looking at stall now because that's what we're really interested in for having the flaps deployed out here at the stall area. So that's right in here. The worst one is the Wortman again. So I wouldn't consider the Wortman for a lightweight ultralight at all as far as having flaps on it. Mine is not as good, so we'll have to take that in consideration. Now some of you who have looked at some of the older design videos, particularly on the UWS-1 ultralight airplane, when I was trying to determine the service area for the horizontal tail, I spent a whole lot of time looking at the coefficient of moment for the wing out here at the stall speed with the flaps deployed. Because frequently our worst case scenario of lift on that tail is going to be at stall. And we don't want to force that coefficient lift on the tail to exceed 0.8. And frequently, stall is our worst case situation, so that's what I was concentrating on. Well, Dan does not use that method to figure out the size of the horizontal tail. He uses the tail volume method. So for this design, we're actually going to ignore the coefficient of moment of the wing at stall in determining the size of the horizontal tail. And we will find out how well that works. So I think it comes down to, out of the 5 that I've got here, I think the selection comes down to my airfoil, Harry Riblet's airfoil, and the Clark Y. Now, if the most important thing for you is to have a high coefficient lift with your flaps deployed, out of those 3, I think it should either be my airfoil or the Clark Y. Harry Riblet's airfoil is just a little bit less by about 5% of the coefficient lift. So it's not bad, it's still pretty good. But if you need to eke out another 5% of coefficient lift, I would say either mine or the Clark Y. As far as stall characteristics go there, I think that my airfoil is just slightly better as far as the way the stall goes, at least out to this point. Past that, I'm not so sure. When you look at coefficient lift versus coefficient of drag, let's come back down here to the 0.6 area. So there's roughly 0.6. So out of the 3 we're interested in, the Clark Y, mine, and Harry Riblet's, the blue one, these 3 in the middle, mine has the least drag, Clark Y has the worst, and Harry Riblet's is in the middle. Now that's drag while we're cruising. That's for the wing itself, but we also have drag due to the tail having to push down. Let's go back and look at that. So that's these three airfoils again. Mine's the green one. Now mine's going to have a little bit more drag out here, 1.5. So mine and Harry Ribbit's is going to have roughly equivalent tail drag. Now in that case, I would select mine over Harry Riblets. But the Clark Y is going to have less tail drag. Now it's possible that this will counter the more drag that it had in our coefficient of lift versus coefficient of drag. But I don't know overall where it would place it compared to these other three. We'd have to do some calculations on that. And by the way, here on the coefficient of lift graph, we really don't care about the stall characteristics too much. I mean, if we had a really sharp drop off, that would be horrible, but these are all roughly the same. Clark Y is a little bit worse. Down here, it really doesn't matter. All it changes is the angle of attack, and that's not really important as far as comparing the two. We just need to know it to set the incidence of the wing. So I would say that since mine and Harry Riblets has the same coefficient of moment at cruse, I'd say mine might be a slightly better selection. Now whether the lower coefficient of moment on the Clark Y would move it up, would have less drag than either one of these. Overall, when you combine it all together, we'd have to calculate that. So at the moment, I'm really interested in finding out how well my airfoil performs. So at the moment, I'm going to go ahead and select my airfoil. When we're climbing, mine appears to have a far lower coefficient of drag than Harry's or the Clark Y. So that's nice. Now down here, this coefficient lift, where you're just climbing just a little bit, mine and Harry's are almost identical, if you can believe this little joggle here. So at the moment, unless I learn something new, I'm going to go ahead and stick with using my airfoil. The next thing that Dan Raymer talks about in his book on page 34 is figuring out the angle of attack when we're at cruse. So here's the equation that he's using. It's a very rough equation, and it assumes a particular slope for the two-dimensional coefficient lift of the airfoil. Now, in my experience, it's actually fairly close for most airfoils. So what we want to know is the coefficient lift at cruse. We've already figured that out, 0.6231. And we'll also work at this lower weight, the Part 103 weight coefficient lift also. And you multiply all that by the quantity of 10 plus 18 divided by the aspect ratio. And if you remember from Part 2, the aspect ratio is 4.5. And then we add to all of that the angle of the two-dimensional airfoil when it's producing zero lift. Well, let's go and figure out how we determine that. Let's go back to XFLR 5. So here we are back at XFLR 5. And in this case, I'm only showing the airfoil that we've chosen. This solid line is using the cruse Reynolds number. This long dashed line is using the stall dash number, and this short dashed line is at the stall Reynolds number, but with the flaps deflected 40 degrees. So where our airfoil produces zero lift is down here at the zero coefficient lift. That's right here. We want to know what that angle is. So if I bring my cursor down here, and then we look up here at the X value, you can see that X is 3.441. So that's what we're going to put in for that alpha. Let's go back to there. So that zero lift alpha is 3.441 with the negative. So if we plug all those wonderful values in and using the cruse coefficient lift at the 517 pound value, we get an angle of attack for our wing of 5.3 roughly, 5.3 degrees. Oh, and by the way, I should mention that for this alpha up here, everything we're doing is in degrees. Now, in some books, they'll actually use radians. You have to be careful and know what units your angles are in, but we're using degrees here. Now, if we use this coefficient of lift and plug it all in there, then that angle for the wing to get the lift that we want at cruse is 4.5 degrees. Now, this gross weight was our takeoff weight. Now, while we're cruising, we're going to be using some fuel up. So our weight will actually be dropping a little bit, which means our angle will be changing a little bit over time. And it'll be decreasing because we won't need quite as much lift. While I'm cruising, this angle that we'll need will be dropping a little bit lower and a little bit lower. Now, I'm assuming that we're going to use about 4 gallons of fuel while we're cruising at maximum. So 4 times 6 pounds per gallon is 24 pounds. So if we take 24 pounds off of here, we're down around 495, roughly, something like that. So let's awfully close to halfway between these two. So at the end of the cruise, we'd be at about 5.9 degrees. So I decided to split the difference between 5.9 and 5.3. So I'm going to set my wing incidence, the angle of attack for that wing, at 5.1 degrees. So it'll kind of average out what I need during cruise. So we figured out one aspect of our airfoil, the zero lift, but we need to figure out a few other things too and write those down because we'll need those in the future. Well, the first thing I'm going to capture is what is my maximum coefficient of lift when I'm stalling. That would be this line right here, and that would be the part that does not have flaps, so that's out at the ailerons, and that'll be this part up here where I have my flaps deflected. So let's do this one first. So it looks like that is, look up here at that Y value for the coefficient lift. Now it's going to be in degrees. So that's 1.695, and that's really not too bad. That's pretty good. A lot of airfoils will be down here around 1.5. Now with flaps deflected at roughly that same angle, let's come up here and look at that. So that's 2.104. I want to capture a couple other things. I don't think Dan is going to use those in his book, but I might want to do a little further analysis. Let's go look at what our parasitic drag is when we're at our cruise angle of attack. And I'm interested in the solid line. That'll be our cruise Reynolds number. Now, if you remember, it was something like 0.62, and that's the 2D, the sectional. So let me put my cursor here at about 0.62. There's 0.62. So my drag coefficient is 0.006. So that's really all I need for drag at the moment. Let's go look at the coefficient of moment. Now that 2D or sectional angle, if I remember right, was roughly 3 degrees. So let's come back down here to 3. That's pretty close to 3, so minus 0.087. I also want to have another thing. I want to know what the coefficient of moment is at stall for both the flapped and unflapped part of the wing. Let's go back and figure out what that stall angle was. That stall angle for the unflapped part is 16.4 degrees roughly. So let's go back to coefficient of moment. So at 16.4, coefficient of moment is minus 0.059, and that's for no flaps. Now let's go down to where the flaps are. So here's the flap line. Let's go back to that 16.3 again. At 16.3 we have roughly minus 0.197. Okay, that's what I wanted to capture for the sectional or two-dimensional characteristics for the airfoil that we've chosen for the ultralight. Well, let's summarize what we've learned so far. We've chosen an airfoil to use, and this is an airfoil that I came up with. In case you're wondering what these numbers are, this number on the left just is a model number. It's just an arbitrary number that I came up with. This is the second model of airfoil I've designed. This 180 means that the thickness of the airfoil is 18% of the cord. This number here, this 3,4, means that that maximum thickness is 30% of the cord back from the leading edge. This 31 means the camber of this airfoil is 3.1, and then the location of that maximum camber is 36.4% back from the leading edge. So that's how that numbering mechanism comes up. So what I can do is just take this airfoil, and if I want to move where that maximum thickness is back and forth, I can use XFLR5, and I would just reset where that number is. If I want to change the maximum thickness, that would just change this number. If I want to change the camber a little bit, that would change this number. And if I want to change that location, that maximum camber, that would change this number. But the overall general shape of the airfoil would still be this number here. Now, all those characteristics that we just captured for this airfoil, I pulled together over here in a single spot, so it's a little easier to come back and find these in the future. And these are the things that we calculated using Dan's equations. So we have our cruise coefficient of lift of the wing. And by the way, I didn't mention it. You'll see lowercase l's over here for coefficient of lift, uppercase L over here. When you see an uppercase L, that's for the wing. If you see a lowercase l, that's for the section or two-dimensional airfoil characteristic coefficient of lift. And then the angle of incidence that I want while we're cruising is 5.1 degrees. The next thing we're going to work on in the next video, which is going to be part 6, is we're going to figure out the horizontal tail size and we'll figure out the vertical tail size. Don't forget, if you'd like to support the channel directly, you can do that on Patreon. There's a link down in the description. And we got a brand new patron supporter recently. And KP, I'd like to thank you very much for becoming an early bird tier supporter of the channel. And if you think you might be interested in that, click on that Patreon link down in there in the description and explore some of your various options. Now, of course, if you're tight on money, that's perfectly understandable. One way you can support the channel is to subscribe if you haven't done that already. And of course, hitting that thumbs up if you like the video. Please go ahead and do that. I mentioned in the introduction that I might do a Part C video, and that's because a viewer on the Part A video asked a question that I thought was pretty reasonable. He asked why I didn't evaluate a single surface airfoil, since those can be fairly light and are common on ultralight airplanes. And since this airplane design is intended to be a cruising airplane, and I want to have low drag, I had not even considered a single surface airfoil, since those are typically high drag. But it would be interesting to compare a single surface airfoil, kind of like the one used on a Quicksilver MX, and my airfoil, which is double-sided, just to see how much a difference there is. So it's possible that I'll do a Part C. Okay guys, thanks for watching this video. I'll be working on Part 6 here before too long. Until next time.